The Subcommittee on Space will now come to order. Without objection, the chair is authorized to declare recess at any of the subcommittee at any time. Welcome to today's hearing entitled NASA's Next 4 Largest Telescopes. I would now like to recognize myself for 5 minutes for an opening statement. In May of this year, the primary mirror for the James Webb Space Telescope arrived in Houston, which is in my district at JSC, for a final round of cryogenic testing, just in time for the hurricane season. These components started a 100-day testing session in a vacuum chamber at the Johnson Space Center, where 3 truckloads a day of liquid nitrogen and cold helium gas chilled the telescope to minus 233 degrees Celsius. That's a total of 300 trucks just for one test. Well, I'm told that Hurricane Harvey complicated things by washing out the roads so bad that they had to improvise a new route to get the trucks to the test facility. I'm very proud of the fine job that the folks at JSC did, working around the clock to ensure the test was a success. I know firsthand the hardships that are being experienced in Houston due to the Hurricane Harvey, and I pray that the recovery for everyone there is going as well as can be expected given the conditions. I would like to add, too, that the new continental rainfall record is in my district of 51.88 inches, and an unofficial record of 64-plus inches. While the 2017 hurricane season has been challenging, this year has been an exciting time for astrophysics. The Nobel Prize in Physics was awarded to 3 Americans that developed the Laser Interferometer Gravitational Wave Observatory, or LIGO, which made the first ever direct observation of gravitational waves, ripples in the fabric of space and time that were predicted by Albert Einstein 100 years ago. I understand several of the potential witnesses for today's hearing could not attend because they are in Stockholm at the prize celebrations. I'd like to congratulate these fine Americans for their outstanding discoveries. Our nation is proud of these achievements. Images from the Hubble Space Telescope are some of the most iconic in history. And we look forward to what is to come from even more capable missions like the Wide Field Infrared Space Telescope, WFIRST. It has been mentioned to me that with Hubble, you could take a single picture into a meeting to show what was discovered. But with WFIRST, you'll have to wallpaper the entire office. The capability has increased 100 times since Hubble. WFIRST is a critical new flagship mission, and we need to make sure that it stays on course. The assets provided to NASA from the National Reconnaissance Office seem like a good fit for the mission, but the program needs reasonable timelines and a realistic budget. It's worth noting that several years ago, this committee proposed that NASA study WFIRST to determine if the assets from NRO would be appropriate for this mission, and whether it would cost more to repurpose existing hardware than to build the observatory from the ground up. Now we face additional questions about the appropriate scope of the mission. The recent report from the Independent Review Committee on WFIRST laid out several options for reining in the cost, and I'm particularly interested to learn more about what impact reducing capability will have on the cost, but more importantly, on the science. I was pleased to see NASA's request for information, or an RFI, announcement on October 12th seeking input from private parties interested in operating the Spitzer Space Telescope and executing the Spitzer Science Program. NASA is looking for partners to continue operating the Space Telescope on their own dime after the NASA mission is completed. I applaud this type of innovative approach, and I hope to see more thinking like this in the future. NASA is currently conducting large and medium mission concept studies for the 2020 Decadal Survey. New concepts like in-space assembly, in-space servicing, and taking advantage of the proposed deep space gateway when developing architectures for very large space telescopes could offer tremendous new capabilities. However, Congress needs to understand the status of the programs today, as well as the plan going forward. Decisions made now can have long-lasting implications on future missions. It seems the smaller principal investigator, or PI, lead missions generally do well at budgeting, scheduling, and cost containment. We need to know that there isn't a systematic or fundamental programmatic problem with how we plan and execute these larger strategic missions. And I'm thankful that our witnesses are here today to help us better understand where we are with these programs and how we plan to move forward. And I look very much forward to hearing your testimony. I would like to now recognize the ranking member, the gentleman from California, Mr. Barra, for his opening statement.
Thank you, Mr. Chairman, and thank you for having another incredibly interesting hearing. And I look forward to learning a lot from the witnesses. I think we can all, remember as children, just kind of laying on our backs in our backyards or wherever we were, gazing up at the sky. And even to this day, on clear evenings, I'll go out and lay and just gaze up at the stars. And my daughter will sit there and say, "Dad, what are you doing out there?" And it's the mystery of what's out there. What can we discover? What don't we know? That is exciting, and it's something that piques our curiosity. And you can see a lot with the naked eye, but really you can see a lot more with the advances we've made in our telescopes. Starting in 1990 with the Hubble Space Telescope, what we've been able to discover in these last 2 decades has been pretty remarkable. Hubble helped scientists pin down the age of the universe, showed us some of the most distant galaxies that we've ever observed. The Compton Gamma Ray Observatory created the first ever all-sky map of gamma ray radiation. The Chandra X-ray Observatory revealed the first ever observations of a supernova remnant. These are all pretty exciting. And if you take Hubble, Chandra, and Spitzer, all provided recently the observations of a neutron star merger detected via gravitational waves by LIGO. Again, pretty remarkable what we are discovering. So I think this is a very timely hearing as we start to think about the next technologies and observatories that let us look into our origins as well as what is out there. In March 2018, TESS is going to be launched, which will build on the success of the Kepler mission to conduct the first all-sky survey of transiting exoplanets from space. Exciting. The chairman talked about James Webb, which will follow Hubble as the next great space observatory, but with 100 times the sensitivity of Hubble. Again, what are we going to discover with that, and how does that continue to propel us forward? We're in the first early stages of the WFIRST program and looking at where that will take us, but it'll give us a much larger field of view to advance the science of dark energy and exoplanets. Again, what is out there? Answering that question, and hoping to propel another generation of folks like myself to just gaze and wonder and enter the fields of science. And we're talking about the next 4 missions. So as we start to think about that 4th mission, how do we learn from the missions that have preceded it, and how do we make sure we engage in an open process, following the decadal survey, looking at that, and really build on what we've learned, make sure we're using all of our resources responsibly, but that we're objectively choosing what that next mission should be. So again, I'm pretty excited about this hearing. I think it builds on what I think is the best subcommittee in Congress, and certainly the most interesting subcommittee in Congress. And with that, I'll yield back.
Thank you, and I do agree. I now recognize the chairman of our full committee, the gentleman from Texas, Mr. Smith.
Thank you, Mr. Chairman. I appreciate both your comments and the ranking member's comments, particularly when you all pointed out that this is a fascinating subject for the American people. They are just riveted by what's going up in space, particularly telescopes that they can see and that are tangible. I might ask the ranking member if he would extend his description of this being his favorite subcommittee to the Science Committee being his favorite full committee, or not. Maybe? Oh, okay. We'll take any suggestions. Mr. Chairman, space-based observations from telescopes like the Hubble Space Telescope have amazed us for decades and expanded our understanding of the universe. We've also seen a rapid increase in the exciting discoveries of planets outside our own solar system. We have confirmed over 3,500 exoplanets and another 4,000 unconfirmed planetary candidates since 1995. Scientists estimate that as many as 11 billion rocky, Earth-sized exoplanets could be orbiting in the habitable zones of sun-like stars in our own Milky Way galaxy alone. NASA's next 4 space telescopes will give us new ways to search for exoplanets and potential signs of life. Each one is designed to build on each other's success. It's an exciting time for astrophysics. The Transiting Exoplanet Survey Satellite, or TESS, is being prepared for launch next year. The James Webb Space Telescope, or JWST, is only a couple of years away from launch. The Wide Field Infrared Survey Telescope, or WFIRST program, is well underway. And we are now in the early stages of designing the next generation space telescope that will hopefully answer many more of our questions about the universe. In January 2016, NASA initiated the 4 decadal survey mission concept studies for the next space telescope that would launch in the 2030s. With the coming heavy lift capability of the Space Launch System, a future space telescope larger than James Webb could be possible. SLS could enable the launch of telescopes that could scan exoplanets for signatures that indicate the presence of continents, oceans, atmospheres, habitable conditions, and perhaps even life itself. The National Academy of Sciences is preparing to undertake their 2020 Astronomy and Astrophysics Decadal Survey. The survey will help inform the Academy about options for future missions. As fascinating as this all sounds, the space program is hampered by delays. James Webb recently encountered additional problems during testing that will delay the mission to as late as June 2019. An independent review board for WFIRST concluded the project is, quote, not executable, end quote, without additional funding or scaling back the mission. And TESS, while still on schedule and budget, experienced a focal shift within the optics of its 4 wide-angle telescopes during testing that may degrade the science it conducts. The issues with JWST are not insignificant. However, NASA expects the existing James Webb budget to be able to accommodate the change in launch date that there will not be an impact on the planned science observations. The remaining work will focus on integrating and testing the instruments, telescope, and spacecraft to prepare it for its new launch date in 2019. More troubling is the report on WFIRST. An independent outside committee established by NASA found that various changes made to WFIRST since it was first proposed as the top-ranking flagship mission in the 2010 Astrophysics Decadal Survey created additional cost and technical difficulties. Apparently, NASA has not learned lessons from its past experiences. After an extensive replanning effort due to excessive cost growth, NASA had to constrain James Webb in 2012 to a congressionally mandated cost cap of $8 billion. Now WFIRST may be subjected to a similar limitation. We cannot allow unbudgeted costs to occur on WFIRST the same way it did on James Webb. The impact to other science missions, as well as other activities at NASA, would be too great. Much better program management and discipline are required to ensure that this does not continue to occur. Last month, NASA instructed the WFIRST program to modify the current design to reduce costs to an earlier target of $3.2 billion. I'm hopeful that the program will find creative solutions to maintain the mission's science objectives. NASA must remain mindful that any potential cost increase of WFIRST will put pressure not only on other astrophysics missions, but also on other agency priorities. NASA should continue to explore options to reduce the cost of these large programs, such as leveraging program surpluses, early-stage cost caps, and firm fixed-price contracts which will benefit taxpayers. Partnerships between the private and public sector in astronomy are well established, and these ties need to be strengthened when it comes to space telescopes. Going forward, I hope that NASA, space companies, and academia will work together to expand public-private partnerships. We are on the cusp of something very significant for humanity, but we are still at the beginning. Many more amazing discoveries await us. Going forward, Congress needs to have the necessary confidence in NASA and its contractors to put us on the right path at a reasonable cost. I look forward to our witnesses' testimony today with representation from NASA, the National Academy of Sciences, the Association of Universities for Research in Astronomy, the Government Accounting Office, and renowned leaders in the field. We have the opportunity to hear a number of valuable perspectives. And with that, Mr. Chairman, yield back.
Yes, sir, thank you. Now, I'd like to recognize the ranking member of the full committee, the gentlewoman from Texas, Ms. Johnson.
Thank you very much, Mr. Chairman, and a good afternoon, and let me welcome our witnesses. This hearing that's being held on NASA's next 4 large telescopes is timely, and today we will receive an update on 3 telescopes that are likely to revolutionize our understanding of the cosmos. 2 of those telescopes, the JWSP and the WFIRST, were the top recommendations of the National Academy's widely respected and highly influential decadal survey process, which was pioneered by the astronomy and astrophysics community in 1964. Each of these independent decadal surveys has involved hundreds of scientists and resulted in an independent peer-reviewed set of recommended science goals and missions to guide NASA's astrophysics program for the next decade. Importantly, the Decadal Survey has also consistently recommended that federal investments be made in a way that ensures a balance is maintained between support for large, medium, and small missions and the research that turns data from those missions into knowledge, new knowledge. While the Decadal Survey process is not perfect, it is this independent, consensus-based process that has been critical to ensuring that Congress supports the priorities established by the astronomy community rather than missions favored by some parties. That is why Congress, in successive NASA Authorizations Act, has consistently directed that NASA's science programs be based on Decadal Survey's priorities. Most recently, the 2017 NASA Authorization Act directs NASA to set science priorities by following the guidance provided by the scientific community through the National Academies of Sciences, Engineering, and Medicine's decadal surveys. The recommendations of the 2010 Astronomy and Astrophysics Decadal are particularly important as NASA works to determine the appropriate scope of the WFIRST mission. I commend NASA for taking time to undertake an independent review to assess the alignment of this mission to the Decadal Survey's guidance and to the goal of ensuring the overall balance of the astronomy program. And in addition, I look forward to hearing about the progress NASA is making in its next space telescopes. I am glad to hear that NASA is preparing for the upcoming Astronomy and Astrophysics Decadal Survey by conducting 4 large mission concept studies for the Decadal Committee to consider during its deliberations. And I note that we only have representation from 1 of the 4 candidate mission concepts here today. I look forward to hearing about the other 3 mission concepts as well today or in the future, as well as because I'm sure they're equally as fascinating. Of course, it is ultimately the role of the National Academies and not the Congress to deliberate the science promise of each of these mission concepts. So I look forward to the witnesses, and I yield back the balance of my time.
Thank you. Now I'd like to introduce our witnesses. The first is Dr. Thomas Zurbuchen, and he is Associate Administrator of Science Mission Directorate at NASA. He earned both his Master's of Science degree and his PhD in physics from the University of Bern in Switzerland. Thank you for being here today. Ms. Cristina Chaplain, good to have you. Our second witness today, She is Director of Acquisition and Sourcing Management at the U.S. Government Accountability Office. She received a bachelor's degree in international relations from Boston University and a master's degree in journalism from Columbia University. Welcome. Mr. Thomas A. Young, our third witness. He's former director at NASA's Goddard Space Flight Center, as well as former president and chief operating officer of Marietta Corporation. Mr. Young earned both a bachelor's degree in aeronautical engineering and a bachelor's degree in mechanical engineering from the University of Virginia and a master's of management degree from MIT. And welcome to you. Our fourth witness today is Dr. Matt Mountain, president of the Association of Universities for Research in Astronomy. He received his degree in physics as well as his PhD in astrophysics, both from Imperial College of Science and Technology, University of London. Welcome to you. And our last witness today is Dr. Chris McKee, professor emeritus of astronomy and physics at the University of California in Berkeley. He is testifying on behalf of the National Academies of Sciences, Engineering, and Medicine. He received his Bachelor's of Arts degree from Harvard and his PhD in physics from the University of California in Berkeley. Welcome to you. I would like to now recognize Dr. Zurbuchen for 5 minutes to present his testimony.
Thank you.
Yes, sir.
Members of the subcommittee, I'm pleased to be here today. And I want to remember that over 70 years ago, Dr. Lyman Spitzer wrote the first scientific paper that explained the practical advantages of putting large telescopes into space. Dr. Spitzer's dream was for large space telescopes. It was actually born in the aftermath of World War II and more than a decade ahead of Sputnik. His dream led to a series of NASA-built space telescopes of increasing size and capability, including one that now bears his name. However, it has not been easy. Placing increasingly capable and complex telescopes in the cold vacuum of space is challenging. Some of NASA's early orbiting telescopes suffered from launch failures. Others had on-orbit issues which limited their lifetime. Several cost more than originally planned, but many were groundbreaking successes and transformed how we look at the universe. NASA has a long history of undertaking large space telescopes that involve significant risk, but include monumental advances in our understanding of the universe and our place in it. Hubble was the first of NASA's four great observatories working together, and in concert with ground-based observatories, these large space telescopes have rewritten textbooks and inspired young people in the US and around the world to study science, technology, engineering, and mathematics, like myself. Along with constructing and operating large facility space telescope, NASA conducts more frequent, smaller-scale principal investigator, PI-led missions within the Explorer program. The combination of PI-led missions and large space telescopes have achieved some amazing results. One example is the study of exoplanets, already mentioned. Thanks to the PI-led Kepler Space Telescope mission, we now know that planets orbiting other stars are very common. Next up is TESS, already mentioned, which was selected in 2013 as an astrophysics explorer. TESS's mission is to discover those nearest planetary systems that have the highest potential for follow-up characterization using telescopes such as Webb and WFIRST. TESS is currently undergoing integration and testing and is on track to meet its launch readiness date in March 2018. An unexpected issue encountered during development was a slight focus shift of the cameras during low-temperature testing. This is due to a previously unknown low-temperature behavior of a material that was used in other spacecraft. The TESS science team has determined that TESS can achieve its science requirements with that shift, and we look forward to its launch next year. We're also eagerly awaiting the launch of the James Webb Space Telescope in 2019. Webb will be the most powerful space telescope ever built, kept extremely cold by a tennis court-sized sunshade in order to detect the infrared light from very faint distant objects. Webb passed a major milestone with the end of cryogenic testing in November at NASA's Johnson Space Flight Center in Houston. The test showed that the mission is meeting its required performance levels. And I really want to also thank the teams at Johnson, which continued the testing in the onslaught that was already described earlier. The Sun Shield and spacecraft bus experienced delays during their integration and testing at Northrop Grumman. Following a schedule assessment of the remaining activities, the Webb launch date was changed from October 2018 to between March and June 2019. And as already mentioned, the existing program budget accommodates the change of that launch date. After Webb's, NASA's next great observatory will be WFIRST. Its purpose is to survey large swaths of sky to provide detailed information on the expansion history of the universe and conduct a large-scale search of exoplanets using gravitational lensing of the light of background stars. In addition, WFIRST will carry a technology demonstration coronagraph instrument designed for the detailed analysis of such exoplanets. In 2016, the National Academy midterm report affirmed WFIRST's scientific promise, but cautioned against allowing the cost of the WFIRST mission to affect the balance of missions and research in NASA's portfolio. Based on the report's recommendation, I commissioned an independent technical management and cost assessment of the project. Upon completion of this independent assessment this fall, I directed the team to find reductions in scope and complexity sufficient to return to the cost estimate, a target set at the beginning of the project. I look forward to seeing the redesigned WFIRST mission concept in February. Thinking beyond WFIRST, we have initiated 4 concept studies for the next great observatory, and I'd be happy to discuss them further. But our understanding of the universe is much richer than it was for the early pioneers of space astrophysics. Our children are looking at the universe differently than we did when we were kids. And this is due to the investment this body has made over the years, and we're deeply grateful for your support. I really look forward to answering any questions that you may have.
Thank you very much, Dr. Zurbuchen. I'll now recognize Mrs. Chaplain for 5 minutes to present her testimony.
Chairman Babin, Ranking Member Bera, and members of the subcommittee, Chairman Smith and Ms. Chairman Johnson. Thank you for inviting me today to discuss NASA's space telescopes. The focus of my statement will be on the NASA's management of the 3 projects, TESS, WFIRST, and James Webb, and what lessons we believe could benefit future NASA telescopes. In total, the 3 telescopes represent an expected investment of at least $12.4 billion and about 50% of the budget for astrophysics. As such, while it is important for NASA to stretch technological boundaries to further scientific research, it is also important to manage and oversee the projects prudently. TESS is the smallest of the 3 projects at $336 million and closest to launch. It has not incurred costs or schedule delays at this point, though it has faced technical challenges. The projected launch date is currently March 2018. As it is in the final phases of development, TESS has been contending with an issue with camera performance, and it faces a risk that its launch provider, SpaceX, may need more time than anticipated to be certified by NASA to fly. This is an upgraded version of the Falcon 9 launch vehicle, and it's the first time NASA is using it for science missions. James Webb, as you know, is the largest and most complicated of the 3 programs, and one of the most challenging NASA's ever undertaken. It's expected to cost $8.8 billion, which is 78% more than anticipated when baselined. Since its re-baseline in 2011, James Webb has stayed within cost and schedule, despite facing a myriad of technical engineering and manufacturing problems. Healthy reserves have played an important role in keeping the program on track, but so have management and oversight practices, which improved significantly after the re-baseline. The project is now in the midst of integration and testing, the most risky phase of its development. NASA recently announced a launch delay from October 2018 to the March through June timeframe of 2019. However, more delays are possible given the risks associated with the work ahead and the level of schedule reserves that are now what is usually recommended. They're below what's recommended. WFIRST is still in the early phases of the development process. It has not yet set baselines for cost and schedule, but preliminary estimates have been ranging from $3.2 billion to $3.8 billion, and preliminary launch dates range from 2024 to 2026. These estimates are under review as NASA responds to the independent review that found that mission scope is not aligned with resources provided. All 3 telescope programs, as well as many other NASA projects, are heeding lessons from the past. For example, we've reported in recent years that NASA's made significant improvements to cost and schedule estimating and oversight processes. More projects are maturing critical technologies before they undertake full-scale acquisition activities. These and other actions have helped NASA to reduce cost and schedule growth over time. As NASA assesses and undertakes the future telescope efforts, there are 4 particular lessons learned that we believe should continue to be heeded. One is taking steps needed to ensure cost growth from a large project does not overwhelm the astrophysics portfolio. The recent W1st independent review was a good step in this direction as it took stock of a large project's business case before the most costly phases of acquisition begin. 2, establish adequate cost and schedule reserves. The current set of telescope projects have generally benefited from having robust reserves to address risks, but this is not the case across NASA. Notably, the human spaceflight projects have all been operating with very limited level of reserves. This has led them to defer work to address technical issues to stay within budget and put future cost reserves at risk of being overwhelmed by the deferred work. 3, regularly update cost and schedule estimates. Programs have been reluctant to update joint confidence levels they establish at their baseline, and there's no requirement for them to do so. For James Webb, an updated estimate may have portended the current schedule delays. 4, enhance oversight of contractors. Much has been done in recent years to better monitor contract performance, but we still find some projects that do not manage contractors well and react only after problems become overwhelming. A program on the scale of WFIRST or James Webb requires good lines of communication, rigorous monitoring of cost progress, insight into contract workforce levels, and having a government presence at contractor facilities, among other actions. This concludes my statement, and I'm happy to answer any questions you have.
Thank you very much. And I now recognize Mr. Young for 5 minutes to present his testimony.
Space telescopes are a valuable and mandatory asset in the scientific exploration of our solar system, our galaxy, and the universe. Space telescopes range in size from explorers to large flagship missions. The 2010 Decadal Survey emphasized the importance of maintaining a balance in the mix of explorers and larger missions. Flagship missions such as Hubble, James Webb Space Telescope, and WFIRST are mandatory to pursue scientific priorities that can only be investigated with large systems. NASA's Explorer program has a rich history of scientific discovery and provides critical opportunities to develop scientists and engineers for the future. The excellence of the United States Astronomy and Astrophysics program cannot be maintained without a healthy balance of large, medium, and small missions. I shall concentrate my comments upon JWST and WFIRST. These 2 flagship missions are in very different phases of their development with very different current challenges. Each mission requires bold leadership to assure mission success. JWST was the highest ranked mission in the 2001 Decadal Survey. Clearly, JWST is one of the most important and challenging civil space missions ever undertaken. JWST has a history of cost growth and schedule delays. It also has a history of development success on a project with significant technological challenges. NASA made a decision a few years ago to fix JWST programmatic issues by budgeting to the most probable cost and scheduling to the most probable schedule. Until recently, performance to this revised plan has been quite good. The current assessment of JWST's status is that integration and test will take significantly longer than planned. The result is a launch schedule delay and the consumption of most of the remaining funding resources. In my opinion, the launch date and required funding cannot be determined until a new plan is thoroughly developed and verified by independent review. The bold leadership I spoke of earlier is required to assure that risk is not added to the program while trying to minimize the schedule and cost impacts. JWST is at a point in its development where the only criterion that is important is mission success. Every appropriate thing that can be done to maximize the probability of success should be done. At this stage of the project, a few extra days or weeks or even months of schedule delay or the expenditure of some additional dollars is a small price to pay to assure success of a mission as important as JWST. Turning to W first, it was the top priority mission in the 2010 Decadal Survey. It was defined as a significant scientific mission with medium cost and risk. However, W first has had requirements creep to the degree that medium cost and risk no longer applies. Each of the added requirements has contributed to the scientific value of the mission, but at a cost. The cost is additional risk, cost, and a potential erosion of program balance that was so strongly emphasized in the 2010 Decadal Survey. The bold leadership I spoke of earlier is required to assure that the most comprehensive and scientifically valuable astronomy and astrophysics program, including W first, is implemented. As the Decadal Survey's highest priority, W first must be successfully completed. The good news is that W first has not reached milestone B. All requirements are currently controllable. NASA is to be congratulated for taking an important step with the establishment of the W first Independent External Technical Management Cost Review. This review has effectively defined the scope, cost, and risk issues for W first. The next step is to decide the scope, cost, and risk appropriate for a top priority flagship mission that is consistent with a balanced astronomy and astrophysics program. I want to emphasize that there is no cause for panic. What is transpiring is a perfectly healthy process to assure that the scope, cost, and risk are appropriately defined prior to proceeding past milestone B. Many studies have shown that the two most significant causes of cost growth and schedule erosion are failure to budget to the most probable cost and failure to control requirements. The history of JWST has been plagued with the failure to budget to the most probable cost. This problem has been true for many space programs. NASA has largely corrected this problem by implementing a policy that requires statistical and independent cost estimating and budgeting to the most probable cost, which NASA has defined as 70-30. W first has been plagued with continual requirements creep. The implementation of a comprehensive independent requirements review prior to milestone B, followed by a rigorous decision process, will mitigate this issue. The process being implemented for W first should become standard for all major NASA projects. I believe NASA has the ability to manage large space telescope projects. Implementing statistical and independent cost estimating, followed by budgeting to the most probable cost, is a major improvement. Prior to milestone B, conducting an independent external review of requirements, cost, and risk that is followed by a decision process that assures the mission is consistent with the Decadal Survey, including a balanced scientific program, is equally important. Following milestone B, requirements must be rigorously managed to prevent requirements creep. Thank you.
Thank you, Mr. Young. Appreciate your testimony. Now recognize Dr. Mountain for 5 minutes to present your testimony.
Mr. Chairman and members of the subcommittee, Chairman Smith, thank you for the opportunity to testify. These are exciting times. The progress of science and technology that's been under the purview of this committee and the Science Committee overall has been quite transformative. We now have the potential, for the first time in human history, to answer a profound question that's haunted us for millennia. Are we alone in the universe? We are at a unique point in our history. As we've heard from Dr. Zurbuchen, we know almost every star we can see has a planetary system. We heard from Chairman Babin what incredible things happened down at the Johnson Space Center, where through a hurricane we showed that the largest space telescope mirror ever built can be made to work at deep space conditions. Consequently, we now know how to build future telescopes, which could have the power for the first time to detect the faint fingerprints of life imprinted on a planet going around another star. And because of investments made by the National Science Foundation on the Gemini telescopes and NASA at JPL and elsewhere, we can now use chronographs to suppress the light from stars and allow us to actually see other solar systems. And we hope to fly the first truly advanced chronograph on NASA's WFIRST mission, laying the technical foundation for imaging Earth 2.0 around another star. We can now bring all of these three advances together, combined with NASA's new SLS capabilities to launch a space telescope that could detect the signs of life on an exoplanet nearly 200 trillion miles away. This would have been science fiction a decade ago. Today, NASA, in one of its 4 studies for future advanced space observatories, is looking at a large 15-meter diameter ultraviolet optical infrared telescope we ungainly call LUVOIR, which, with the right commitment, could be ready for launch by the early 30s. Now, why is such an ambitious telescope with a mirror almost 3 times the size of James Webb required? First, we have to realize how faint another Earth orbiting a neighborhood star would be. This image, which you can see from here, of course, was taken by NASA's Cassini spacecraft. We already see at a distance of 900 million miles, all we see is a faint blue dot. That, of course, is us. At a distance of over 200 trillion miles, that's over 30 light years away, an Earth-like planet is an incredibly faint object. In fact, fainter than the faintest galaxy in this Hubble Deep Field. And then we have to understand what we're looking at. You would think with 10 to the 23 stars in the universe, that's 1 with 23 zeros after it, you would think that life exists somewhere else. Statistically, that should be the case. However, if you talk to biologists, these optimistic statistics tell us not so fast. The only place we know life exists is here on Earth. And the only way to actually determine if life exists elsewhere, to find out how unique we actually are, is to go out for ourselves to see. And this is exactly what NASA now has the capabilities to do. But finding one Earth-like planet won't be enough. We already know 2 Earth-like planets in our own solar system where there are no visible signs of life, Venus and Mars. So we're going to have to examine hundreds of exoplanets, hunting for those faint signatures of life to find out if habitability exists. If there are habitable planets orbiting around stars near a sun, telescopes like the LUVOIR concept will certainly find at least one. If a LUVOIR does not detect any signs of habitability, we will know that life as it exists on our home planet is extremely rare. This too would be profound, if a somewhat lonely discovery for humanity. NASA, and uniquely this nation, has laid the foundation, both scientifically and technically, for such a transformative tool for space astronomy. And this is a telescope we can actually now build because of those investments. And it's important to state, without the leadership of NASA's Space Mission Directorate, exemplified by Dr. Zurbuchen here, and with the support of committees like these, none of this would be possible. We would not be sitting here today making this case. So let me make an audacious claim that the discovery of extraterrestrial life would profoundly change history. Apollo's 8 iconic image on the left of the Earth from the moon established the United States as the leader in space science and exploration that inspired every generation since, including myself. The discovery of a living planet elsewhere in our galaxy, like this artist's concept on the right, would have as profound an impact on the 21st century as Neil Armstrong's first step would have on the moon. And it is this quest that only NASA is capable of doing. Recognizing this committee and Congress added the search for life's origins, evolution, distribution, and the future in the universe to NASA's Authorization Act. If we can build on this vision, we can carry the spirit of Apollo into the galaxy. And let me briefly finish. As Carl Sagan so eloquently said, when our far descendants, perhaps centuries, even millennia in the future, look back at from their new home planets and hunt for that pale blue dot in the sky, that was us. They will wonder how humble, how fragile were our beginnings, how many rivers we had to cross before we found a way. With American vision, with American leadership and optimism, we can find a way. Thank you, Mr. Chairman.
Thank you very much. Now I'd like to recognize Dr. McKee for your testimony for 5 minutes.
Chairman Babin, Ranking Member Bera, Chairman of the committee Smith, and Ranking Chair Johnson. Thank you very much for the opportunity to appear before you today in my capacity as a member of the Committee on Astronomy and Astrophysics, the CAA, of the National Academy of Sciences, Engineering, and Medicine. CAA is one of 5 subcommittees of the Academy's Space Studies Board that span the science disciplines supported by NASA. Each of the 5 subcommittees is charged to assist the federal government by providing advice on the implementation of decadal survey recommendations. As you know, the National Academies decadal surveys, which are mandated by law, provide NASA with consensus advice from the scientific community on proposed science priorities for the decade ahead. I have the honor of serving on the CAA, and I was also one of the co-chairs of the 2001 Decadal Survey in Astronomy. The highest recommendation in our report was the James Webb Space Telescope, JWST, a truly remarkable feat of engineering that is expected to deliver groundbreaking scientific capability beyond that envisioned when we recommended it. Chairman Babin, I would like to thank you and the committee for giving me the opportunity to present to you today some of the perspectives on the status of NASA's program in astrophysics, drawing in particular on the Academy's 2016 report, New Worlds, New Horizons, a midterm assessment. This report concluded that already in the first half of the decade, scientists and teams of scientists working with these cutting-edge instruments and with new capabilities in data collection and analysis have made spectacular discoveries that advance the NWNH vision. While these discoveries are really remarkable, the fact that they occurred is not. The Congress, the executive, and the research community have relied on the independent and non-advocacy convening power of the National Academies to develop a national consensus on which science space missions NASA should pursue. This process, over a period of nearly 60 years, has led to the United States developing clear leadership across all the fields of space science. This is why the Congress has repeatedly instructed NASA and the executive to use the decadals as the foundation of the agency's strategic planning in space science. An essential feature of the decadal process is that it involves a broad cross-section of the community. In the case of the 2010 Decadal Survey in Astronomy and Astrophysics, the Academies appointed nearly 200 astronomers to the survey committee, the supporting panels, and the working groups. Hundreds of additional astronomers provided input. In fact, I would venture to guess that a significant fraction of the entire astronomical community participated. The committee then undertook the hard and painful task, which was necessitated by the relatively severe financial constraints under which the agencies were expected to have to operate, of prioritizing the many exciting and realizable activities presented to it. Mr. Chairman, today NASA is implementing the Decadal Survey. The Wide Field Infrared Survey Telescope, WFIRST, which is the 2010 Decadal's highest-ranked large space telescope, is, quote, designed to settle essential questions in both exoplanet and dark energy research and will advance topics ranging from galaxy evolution to the study of objects within our galaxy, end quote. The midterm report underscored the continuing scientific case for the pursuit of this mission. The report noted that implementation of WFIRST with a larger mirror than envisioned at the time of the decadal's prioritization, with larger infrared detectors, and with the addition of a coronagraph makes WFIRST an ambitious and very powerful facility. However, because the risk of cost growth in WFIRST could distort the NASA program balance and limit options for the next decadal survey, the midterm report called for an independent and technical management and cost assessment of WFIRST. That assessment has been carried out, and the descoping effort is now underway. Meanwhile, it's also worth noting that the midterm report endorsed NASA's plans for executing the second priority recommendation of the 2010 decadal, the enhancement of the Explorer program. The Explorer program is currently supporting the development of the Transiting Exoplanet Survey satellite TESS, which is scheduled for launch next March. NASA is also implementing the third and fourth high priority recommendations in partnership with our European colleagues at ESA through participation in the Athena X-ray telescope and in the LISA Gravitational Wave Observatory. LISA will open a new window on the cosmos by measuring the ripples in space-time produced by the merger of black holes, which are far larger than more massive than can be detected with the NSF-supported LIGO facility. That facility has confirmed Einstein's theory of gravity and solved the mystery of the source of many of the elements in the periodic table beyond iron, such as gold and uranium. The next decadal is expected to start in about a year's time. And at the CAA, we have heard how NASA is supporting teams of astronomers and engineers to develop mission concepts for both flagship missions and moderate-scale missions. This methodical approach to preparing the community for the decadal is, in my personal opinion, vitally important. The CAA is at the same time preparing to release the first call for white paper inputs from the community in advance of the survey so that when the chair is appointed, she or he will have fresh community input on the science for what is nominally called Astro 2020. Mr. Chairman and members of the committee, the bottom line result of the decadal survey process in astronomy and astrophysics, and indeed in all the scientific fields supported by NASA, is that the United States has reaped the benefits of this community-based process that the academies conduct on behalf of the nation under its unique charter from Congress. I'm here today to discuss why this process works as well as it does and to answer any questions you may have. Thank you.
Thank you very much for your testimony, Dr. McKee. The chair would like to recognize himself for 5 minutes for questions. Dr. Zurbuchen, NASA indicated that the delay to JWST is a result of issues identified in integration and testing, but there was also a potential conflict in French Guiana with the European Bepi-Colombo mission. Why was the decision made to launch the $8 billion JWST on the European Ariane 5 rocket instead of a reliable U.S. launch vehicle? Was cost the only consideration, and what are the risks associated with the transporting of JWST to the European launch site located in South America and French Guiana?
Thanks for your question, Mr. Chairman. Part of the decision to go with this other launch vehicle, of course, was cost. And at the moment in time, you remember, of course, I was not sitting here when that decision was made. Cost was an important factor, but so was international collaboration that is really part of the James Webb Space Telescope. As part of the telescope itself and instrument there, we have important international collaborations that really contribute to the leadership that we have in space astrophysics. So kind of we don't believe that there's a conflict of leadership for the United States and some of these collaborations. I will submit, if so desired, Mr. Chairman, more information for the record on the details of that decision and all of this. You should know that the path to that launch site has been under consideration, and in detail, I've heard a briefing for every part of that, and we understand what the risks are in detail and comfortable with it.
I understand they're going to have to even change bridge heights and things like that. Is that the case?
There's a number of things that we had to do for a variety of testing with Webb. Some of the tests we actually wanted to do in some other districts we didn't do because of bridges. In some cases, yes, some bridges might be lifted, or some roads will be enlarged for that. Again, I'll provide the details.
Right. One of the lessons learned that GAO highlights is the need to manage cost and schedule performance for large projects to limit the impacts to the entire science mission portfolio. What ways can NASA balance its portfolio better and ensure that problems in large programs do not overwhelm the smaller ones without losing sight of science objectives, Dr. Zurbuchen?
I believe that what we did with WFIRST is exactly what we should be doing to ensure that balance. I mean, I'm committed to keeping that balance in place through the astrophysics portfolio as well as the other disciplines where similar recommendations are provided from their respective decadals. And I believe that what is required, especially prior to key decision point C, which is what Tom Young talked about, it's absolutely important to create management processes to make sure that these missions don't blossom without boundary, without limit into bigger missions. So the independent review as well as the action that I took is precisely motivated, not because of anything that we don't like about the mission, but motivated by the importance of creating that balance and keeping it for the years to come.
Okay, thank you. Now, Dr. McKee, the cost estimates for both JWST and WFIRST increased drastically from the time the academies recommended them as part of the decadal survey. Does the academy provide any recommendations on the maximum cost a program should grow to before it compromises other astronomy and astrophysics priorities? And does the academy recommend any capabilities to de-scope if problems are encountered during formulation or development?
Let me begin by discussing the first of the projects you mentioned, James Webb. At that time, we did not have the cost control measures that NASA has implemented since. And as I think has been noted, there was a drastic increase in the overall cost of that mission. At the time of the 2001 decadal survey, we did not anticipate such a cost growth. By the time of the 2010 decadal survey, there was a much greater awareness of the impact of these large missions, and as a result, that decadal survey considered several different scenarios for the budget of the program. And however, to my knowledge, they did not explicitly put in any hard and fast rules as to how you would de-scope. When as the issue of the problems come up with the NASA budget, the importance of maintaining a balanced program is very high on the priority list for the academies, and they have been working with NASA to try to maintain that.
I have several more questions, but I'm out of time, so we're going to go to the gentleman from California, the ranking member, Mr. Barrow.
Thank you, Mr. Chairman. So in my opening comments, I talked about, just gazing at the sky, and, what Hubble allowed us to do was those fuzzy patches that we see out there prove that those galaxies full of millions or billions of stars existed. It also proved that the universe was expanding. I guess Dr. Zurbuchen, as I'm thinking about, TESS, James Webb, and WFIRST, science building on itself, I just want to make sure, with TESS, we'll do that all-sky survey. We'll learn more about exoplanets and find more exoplanets. With James Webb, am I understanding this correctly? We'll look sometimes backwards in time and look at star formation and trace the evolution of these galaxies from birth to death and learn much more about our universe. And then in the WFIRST program, it's this dark energy that is expanding our universe, and the purpose of WFIRST is to better understand that dark energy, as well as continue to learn more about the exoplanets that are out there. As we search for life, as we search for what else is out there. Am I thinking about that correctly? One building on the next, each mission informing the next mission. For those folks that are watching at home, because I know they're riveted to their televisions, trying to figure out where we go next. And so if we're building one mission on the next, as we think about the decadal survey, which is our objective way of, much as decadal informed us to do James Webb, decadal informed us that we should focus on WFIRST. You touched on the four possibilities going into this next decadal survey, and would you briefly just go over what those four?
So first of all, Congressman, of course, you're really well informed about how these spacecraft relate to each other and how they're really building on top of each other. You could not imagine W first without the Hubble being there, kind of doing the kind of work, because what we're really doing is looking at kind of the big data version of a Hubble, which is 100 times, bigger in terms of many dimensions, right? But including the data that are coming down for us to mine and really look at these large-scale structures that are out there. And talking about the science overall, what is the universe made out of? Things we call dark, just because we don't know what they mean, really. So the next four that are under consideration, first of all, is a concept called HAPEX. You heard, Dr. Mountain talk about LUVAR. Just like LUVAR, HAPEX is really focused on habitability. So it's focused on looking at, with a slightly different concept, but it's looking at emissions that come in atmospheres from planets that would tell us about both the physics of these atmospheres, but also whether there's something there that could hint towards the presence of life. So those are the two that are there, HAPEX and LUVAR. Then LYNX is a next generation X-ray surveyor. So there, what we're looking at is really the energetic part of the universe, really kind of in X-rays and gamma rays, looking towards at the next generation of looking at these physical processes that you talked about Chandra, or it was talked about, kind of really looking at the next generation of physical processes that really help us understand how energy actually gets created, how they, in some of the weirdest places in the universe. And then the final one is Origins. It's a system that's really following matter around dust and kind of elements of the type that we discussed as part of this unique event there. How are these transported around? Really talk about kind of the origins of these contributions to stars, and then what of course could create habitable planets as well. So those are the three missions, looking at a variety of spectral ranges, looking at a variety of centers that actually where these the teams are rooted.
So all of these, in an ideal world, we'd have unlimited resources, and all of these missions would provide us vast knowledge and help us. And again, our way of guiding Congress as well as NASA in a purely objective way is to do the decadal survey, to take this group of scientists and experts, who have much more knowledge than, we're a pretty smart body, I think, but who have much more knowledge and expertise than we do, and give us guidance. Is that an appropriate, high level?
Absolutely. One of the jobs that I don't have is to prioritize which one is the most important one, and you don't want me to have that job. And the simple reason for that is if there's another person sitting in that chair, the whole strategy changes. So we really believe, and I'm a strong believer in the wisdom of having a process like the National Academies Insights really driving us, because what that creates is constancy of purpose, and it creates success in systems, in projects that actually exceed the time frame of any one of us in any of our respective positions.
And would you say the decadal surveys has served this body as well as NASA and the scientific community well?
I really do believe so, and you should know, kind of before I went to NASA, I was actually actively involved in some of this advisory structure and saw from the inside the kind of high quality of deliberation and the high quality of decision-making that's going on there. So I really believe in it, and I rely on it every day.
Great, thank you, and I'll yield back.
Now recognize the gentleman from Alabama, Mr. Brooks.
Thank you, Mr. Chairman. My questions are directed at Dr. Zurbuchen, but if anyone else wants to chime in, feel free. In September 2017, following a schedule assessment of remaining integration and test activities, NASA announced that it was planning to launch the James Webb Space Telescope between March and June of 2019, a 5 to 8 month delay from the previously planned October 2018 launch readiness date. Given current technical challenges, new information gained from recent deployment tests of the Sun Shield, and remaining work to complete, to what extent is the current expected launch readiness window of March 2019 to June 2019 achievable?
At this moment in time, with the information that I have, I believe that it's achievable. But I actually believe that what Mr. Young told us about an independent review is exactly what we should be doing. And frankly, I have directed the team to do just that in January. The reason I do it in January and not right now is we're going through fold number 2. Remember, what we're really spending time on right now is practicing how to unfold. We want to get this right. And so basically, we went through fold number 1, which took us a lot longer, which to a large extent, together with the propulsion system issue, also at the contractor, basically contributed to the majority of the delay. Actually, the only real delay that was on the outside of the schedule reserve that we had.
Hey, Dr. Zurbuchen, you've already answered my question. I wasn't asking for the causes of delay to date, just what the future looks like.
I apologize.
Next, when will the agency announce a specific launch readiness date within this window, and how will it determine that this new launch readiness date is realistic?
I will submit the exact date for the record because I want to have a schedule from our project office to really make sure that the review is actually can be done at the right time. I'll submit it for the record. My guess is kind of in the January, February timeframe, but I don't want to commit to that before I really talk to everybody involved.
Thank you. Next, the Government Accountability Office testimony states that the Transiting Exoplanet Survey Satellite, also known as TESS, program no longer has cost reserves to cover a delay past March of 2018. What does that mean for the project, and how does NASA plan to fund a test launch if it is delayed past March 2018?
We expect to solve the problem, with, talking to, through the processes that we have to deal with this kind of unexpected expenditure and basically deal with any delay that will come, because it would not be to the fault of the project itself. It will come from the outside.
In March next year, NASA is planning to launch tests on the Block 4 version of the SpaceX Falcon 9 rocket. SpaceX has experienced 2 mishaps in the previous 2 years with its Falcon 9. In June 2015, a Falcon 9 rocket was destroyed while it was carrying a Dragon cargo spaceship loaded with supplies bound for the International Space Station, and in September 2016, a Falcon 9 exploded on the launch pad while loading fuel for a routine engine test, destroying a commercial satellite. In light of these mishaps, what remains for NASA to certify the Block 4 version of the SpaceX Falcon 9 rocket for the purposes of launching the test satellite?
So I was updated earlier this week that the certification type of meetings, are scheduled for the early next year and basically involved a series of interactions with the contractor and really external views of various systems and subsystems. At the completion of that, I really trust our, the part of our agency that's doing that. I will ask them directly, is it safe to launch? I'm waiting for that process to come to its conclusion.
Do you have any concerns or reservations that the Block 4 version of the SpaceX Falcon 9 rocket will not be certified in time for tests to launch in March of 2018?
At this moment in time, I don't have any such concerns.
All right. Thank you, Mr. Chairman. I yield back the balance of my time.
Yes, sir. Thank you very much. Now, Ms. Johnson has left. I recognize the gentleman from Colorado, Mr. Perlmutter.
Thank you, Dr. Babin. So I want to start quickly with Starshade, and because I do have a prop, which is like that, okay? So it helps to, let's go this way. No, that's better. And I shouldn't put it in front of my face. That's not a good idea. But Dr. Zurbuchen, can you tell me about Starshade and about the use of both the Academy as well as universities in working with NASA to make sure that Starshade provides value and helps us see even more distant objects?
The Starshade technology, together with the coronagraph technology, of course you're aware that Starshade technology was invented in Colorado.
At the University of Colorado,
exactly.
Yes.
I met
Go
the
Buffs.
guy. He's an amazing guy, right? It's more than one invention, of course. It's not the only one. But together with coronagraph technology, Starshade technology is a really good way of actually covering up the light of the star to really actually blend out that kind of flood of light so we can see the few photons, you know, the faint light that comes from planets. And so basically, in many ways, it's a very elegant process. It's basically a big shade of the shape that you had there that is perhaps 30 meters or even larger, depending on the geometry, is flying 10,000 kilometers ahead of the telescope at really accurate location, and actually uses kind of the properties of optics to blend out at the right point at the telescope, the star, to very, very high precision. Coronagraphs are very different. It's much more like a thumb in the camera. Like we use it when we look at the sun. It's taking light away kind of internally. Again, a lot of advances are being made there, some advances even today. So both of these technologies are being developed right now through the technology investments in a variety of places, including universities, including within NASA or the organization that Dr. Mountain leads, to really look at what the right way is. My prediction is, as we go forward in this very new field, that on a timescale of 5 to 10 years, if we have a hearing like this, again, there will be even additional technologies that will be proposed, that additional ways to solving this really important problem.
So, and I would just encourage you, and I imagine Dr. McKee and Dr. Mountain would agree, to continue to, partner with the academy, with the universities, as you expand this science. Now, what I really want to talk about, I'm going to focus, Mr. Young, to you and to Ms. Chaplain. Dr. Mountain mentioned earlier a number with 23 zeros behind it. The number I have in mind isn't that big, but it's big. So, right now, we're dealing with a tax reform bill, the deficit of which is $1.5 trillion. That's what the Budget Office predicts from the House version of that. And it's a number that has 12 zeros after the first, so it's 12 digits. So just, Ms. Chaplain, help me with the math. You've helped me with other budget issues in the past. And so do you know what the NASA budget is this year?
It's, the budget request is about $19 billion.
All right, so let's make it easy, round it up to 20. Okay, $20 billion. That $1.5 trillion hole in the deficit is 75 years worth of NASA's budget. Okay, let's go to something else. How about, you said we've got a potential, or we have a cost overrun on James Webb. Initially a $5 billion projected project, now it's up to 9. How many James Webb telescopes could we build for this budget loss we're going to take of $1.5 trillion? Can you do the math in your head?
I probably can't do it that quickly, but it's a lot of telescopes.
Well, let's say the telescope booms up to $10 billion in cost. That's 150 of those.
Yeah.
Okay? Now, you know what's near and dear to my heart? It's getting our astronauts to Mars. And you and I have had a lot of conversations. Mr. Young, you and I have had a lot of conversations. And at one of our hearings, the number of $200 billion over the next 16, 17 years was suggested by NASA. So let's do the math on that one. How many times could we go to Mars for this deficit that's coming from this tax bill that the Republicans are proposing? I'll do it. It's a rhetorical question, but about 8. And that's starting from scratch. So these numbers are big, and we need to manage these projects the best possible way we can. But on the other hand, when we do things like we're doing this week and over the next few with this tax bill, we potentially hurt your agencies and a lot of others. And we don't need to inflict wounds on ourselves like that. And with that, I yield back.
Thank you, Mr. Perlmutter. I would remind the crowd out here that there's some of us hoping that we will have enormous growth with this tax bill. We will now go to the gentleman from Florida, Dr. Dunn.
Thank you very much, Mr. Chairman. I'd like to turn our attention to some of the life sciences that NASA gets involved in. In the 18 appropriations bill, as marked up in the committee, we inserted a provision for NASA to spend at least $10 million on life detection technology. Can you explain briefly, whoever's the right person here, for what are we using for life detection technology? Maybe tell me a little bit about how that compares to the older and what we're developing. Briefly, 5 minutes.
Why don't I get started? So part of the life detection technologies are actually the type of technology we already talked about here. So it's basically star shade, it's coronagraph technology, as well as other promising approaches that would really help us to actually collect a spectrum and kind of the type that was shown here by Dr. Mountain, you know, like a spectrum that would help us kind of read, if you want, a fingerprint of life elsewhere. And so it's that kind of technology that we're currently investing in and are committed to doing so in the future.
All right, so life takes some pretty surprisingly different shapes and forms. Can be a little hard for us right here on Earth to decide what is life and what isn't life. And I wonder if we are needlessly or unnecessarily limiting the search for the type of lives we might find on an exoplanet.
I think it's a really hard question you're asking. Kind of what we know about life is what I would always talk kind of in science language as an n=1. So we have exactly one type of life and many variations thereof. And so basically what we're doing as scientists, you know, and there's people who are scholars in this, perhaps even at this table, what we're doing is we're going the other way and really asking, what does the universe provide us with? You know, kind of from, in many cases, basic principles, kind of early universe, but how stars work, what are the building blocks, and how can life, what would be the principles that we would be using from these building blocks that basically would actually create signatures kind of in many different scenarios that are actually different than ours, that we could really see. So it's not so much how exactly what life does, but what life is, but what life does on an atmosphere and so forth.
That's good. So can you explain why it is to the public in general? Why are we so fascinated with looking for life? And I don't want an essay answer here. Have you got a sound bite for me back home?
For millennia, we've wondered where our origins come from. You know, are we alone? I mean, for 4 billion years, we've looked up at the sky and wondered, are we alone? And that loneliness may come to an end if we discover that we are no longer alone. That would change the way we think about biology, change about our civilization. And if we find nothing, think how precious this planet is.
So one of the ways we can spend some of this $10 million is on looking for life on Mars, with whether manned or unmanned missions we send there. I know we've done that in the past. I know that the answers have been cloudy, murky, but I think there's ways to rather inexpensively clean up those experiments and rerun them with several Mars landers that are coming right at us. Because of the time, I'm going to skip to the next question. So there's we propose 4 telescopes here, gentlemen. So why 4? Why do we need 4 different scopes to look at the exoplanets?
I just want to make sure, I assume you're talking about telescope studies for the future, the 4?
Right, yeah.
So my full expectation is that through the academy process, a prioritization will come. So by us focusing on 4, basically what we hope to do is provide a set of options for the academy to really put the pieces together and actually really see what's possible, kind of really translate, kind of, if you want, scientific aspiration into some engineering language and help from that, based on the scientific knowledge we have at that point during the decadal.
Are you telling me you might cut down to launch less than 4, launch 1, 2, 3?
The 1 will be the first one out of the 4. We'll not do 4 at the same time.
Oh, I understand. I mean, which seems funny to be planning for 4 all at once. So, and in the few seconds left to us, why are we launching the James Webb on the Ariane? I understand the cost things. Is it just cost? Why are we using a European missile rather than a good old-fashioned American rocket?
It's a really good question. I already promised to submit that answer for the record and really go through the history of this. I told you what I know from that.
So good, yeah, and so I'm a physician. I'd love to get involved with you guys in your life science, your proof of life, if you will, on whatever planets we land on. And I yield back. Thank you very much.
Yes, sir. Thank you. I don't believe there's any more Democrats. Let's see. Mr. Higgins from Louisiana, 5 minutes.
Thank you, Mr. Chairman.
Sir.
Mr. Mountain, Dr. Mountain, my questions will be directed to you. I'd like to jump right into the next generation of space telescope and space technology as you envision it from your unique perspective, sir. Over the last several years, microbial life, microorganisms have been discovered to be quite resilient living in space on the exterior of the hull of the International Space Station and in experiments within, within minerals and rocks. Do you envision the next generation of search for life throughout the cosmos with our next generation telescopes? Do you envision them to be able to measure that spectrum by the wavelengths that we study and search for microbiotic life, as given the fact that the Hubble's been up there for quite some time, and our future telescopes have been under development for quite some time, and yet it's only recently that we've discovered microorganisms on the hull of the International Space Station itself?
And again, I can refer to my colleague, Dr. Zurbuchen. I mean, it's a very good question. So the issue is that all those microorganisms, whether they're in the space station or in the depths of the Chernobyl reactor or on these deep sea vents, they've all come from one place. It's Earth, this N=1 problem. And we know that this type of bacteria affected the atmosphere of our Earth roughly 1 billion years ago and created the oxygen that we now breathe. And so that was the signature that if we had been on another planet and looked back, we would have seen. The problem is Earths, as I've tried to say, are very faint. We haven't had the power and the capability to look at another Earth-like planet. And I think that the power of this whole idea from NASA's perspective is it isn't just looking around other stars. NASA wants to go to Europa. It wants to put people on Mars. All of those are potential places where life could have independently come, not just come from our Earth.
Specifically, speaking of next-generation telescopes, which is trying to stay within the parameters of the purpose of this particular committee discussion, and the search for life by investing massive sums of the people's treasure, we're discussing microorganisms and the search for them. What about silicon-based life, which has been a great deal of scientific discussion about that recently? And do you envision in next-generation telescopes the ability to detect silicon-based life?
Again, it's as Dr. Zurbuchen said, we don't yet know what silicon life would look like. And which is why we believe that the only way to look at this is to analyze the whole spectrum of another Earth-like planet, to see things we don't expect, and then try and build up models. What we understand about life is that carbon and water and oxygen are pretty essential. We don't yet know what silicon life would look like. I don't know if, Thomas, you had any further, but we haven't yet found a way to recognize what silicon life would be like.
Thank you for that answer. In the interest of time, I'd like to jump into what your thoughts are regarding dark matter or dark energy as they relate to current and next generation telescopes. Dr. Mountain, again, the telescopes we're discussing investing massive amounts of money in will be embedded within the dark energy or dark matter that we call it that because we don't know what it is. Do you envision this next generation of investment to be able to measure that in some way and give us some answers as a people, be we Democrats, Republicans, or anything in between? We would sure like to know what dark energy and dark matter is.
As would we scientists. I mean, we are in that fortunate or incredible time where we're using telescopes like the Hubble and other telescopes. We've discovered we haven't understood where the matter comes from. That's dark matter. We haven't understood where the dark energy comes from. That's 75%. And that mystery is what's driven space missions like WFIRST. We're hoping to be able to measure across the whole sky these very weak effects and give us real insight in what physics are we missing. How is it that we sit in 2017 and we have to say to you, we don't understand what 95% of the universe is.
Exactly. And, Mr. Chairman, my time has expired, but should any of the other panel members have input, please, we would like for you to submit your answers in writing regarding the considerations of dark energy. I yield back.
That's very fascinating. Thank you for those questions and answers. Absolutely. I think that's the first time I'd heard of Silicon Life. I don't want to run into one of those critters anytime soon. Now I'd like to recognize the gentleman from Indiana, Mr. Banks.
Thank you, Mr. Chairman. Harris Corporation, located in my district, has provided vital technical support for both the James Webb Space Telescope and the Wide Field Infrared Survey Telescope, which we are very proud of, coming from Fort Wayne, Indiana. My first question is for you, Dr. Zurbuchen. NASA has put a great deal of time and money into the development of the Webb telescope and has the potential to expand on the discoveries of the Hubble telescope. However, since it will be launched into an orbit that makes astronaut repair impossible, it's important that the complicated process of building and launching Webb is done the right way. Do you believe that Webb can be launched and deployed successfully and achieve its objectives?
You're talking about, so do I believe that Webb can be launched successfully in the year? Yes, I do.
Okay.
So I believe that the work has been done from all aspects, looked at multiple times. Webb can be done successfully. I'm going to be really nervous during that time, as I always am. Every time I look at the launch now, I'm nervous, but yes,
Okay,
I believe
good,
so.
good answer. The missions that we're discussing today are very large in scale. This large scale makes these missions expensive and complicated. Is there any consideration, Doctor, at the agency to utilize the growing expertise in small spacecraft to accomplish some of the goals being discussed here today?
Absolutely. I mean, so there's a number of approaches that we're looking at, many of them actually on the outside of astrophysics, just because there's many more photons around. The light is much stronger when it comes from the Earth, for example, or from the sun. And so there's a number of approaches that we're looking actually as part of an initiative that I launched when I came to NASA to really look at these systems. And as we go forward and learn how to fly these spacecraft, perhaps they become more relevant for astrophysics on a timescale of 10, 20 years. We don't know. At this moment in time, most of the applications are elsewhere, but even in astrophysics, we're starting to look at them.
So you would agree then that we could reduce mission cost and duration by utilizing small spacecraft?
In some of the cases, the answer is yes. In some of the cases, like the one with the exoplanets, right? It's the bucket size, how big the telescope is really important, because that's the most important driver. So at this moment in time, with the technology we have today, anywhere, we don't know how to use small spacecraft for that, because it's basically, we don't know how to span up a mirror of that size. But, you know, I'm sure there's smart people either in your districts or elsewhere that will think about this and really try how to use small spacecraft flying, information or otherwise, to learn how to do this. I don't know what's going to happen there. Right now, we can't.
Good. So it's clear that the projects we're discussing today have the potential for very exciting discoveries. Does NASA have a plan to do outreach to middle and high school students in order to get more young people interested in NASA and space exploration?
Absolutely. We're committed to telling our story to all learners of all ages. And I'm personally very excited about middle school and high schoolers. Of course, I have children that age, but also just because I see how much knowledge like this can really impact their careers and their lives. So yes, we're committed. Our programs are doing that now, and we commit to doing it in the future together with our partners, many of which here at the table.
Thank you very much. I yield back.
Yes, sir. Thank you very much. I'd like to now recognize the gentleman from California, Mr. Rohrbacher.
Thank you very much. I apologize for just coming in now. I was chairing my own subcommittee hearing downstairs, so I apologize. But I will be reading your testimony. I think that the idea of space telescopes and also just the whole idea of astronomy is so important that it's hard for people to grip, come to grips with how important it is for us to know what's going on out there, because it sets down, well, anyway, I don't have to explain it to you. You're going to be explaining it to me. But with that said, there's one element that I'd like to talk about, and I don't know, I understand it has not been discussed, and that is, I think one of the things that behooves us to work and to have a system that we can identify things as far out as we can go and learn the fundamentals of the universe, but also see if there's something out there that could be harmful to us. And we just had, and I don't know if it's still there or if it's gone by, an asteroid that was, what, 3 miles wide, that was just within several million miles of the Earth. We need to have a system that we can identify anything coming towards the Earth that may well hit the Earth at least 5 to 10 years out. Now, Arecibo telescope was almost shut down about 10 years ago. They almost closed Arecibo, and Arecibo, it's my understanding, is at this point essential to making sure we can identify an object and then track it so we know whether it's actually going to hit the Earth or not. But we need to make sure that capability is built into our satellites and our telescopes that we're going to be putting into orbit, so that they are also expanding our understanding of the universe, but they're also, they are our guards. They are the sentries, you might say, looking for danger that might be heading in our direction. Now, is that, I don't know if it's been discussed, but where do you see that in terms of our planning for what type of telescopes and things we will be doing in the future? And I don't know who to ask, but whoever would like to comment on that.
Congressman, the Planetary Defense Program, which is what you're relating to, is part of our planetary division and is multifaceted. And like you correctly said, Arecibo is an important part of that because it helps us characterize objects that are really near Earth, because we can bounce off, radiation off it and actually look at it at Earth. There's many other assets that we're using, both ground-based and space-based, that are there, and actually we're looking at, as we go forward, actually even assets that are that Dr. Mountain and his organization is working with to really, in fact, provide that kind of information. You, of course, are aware of that interstellar object that was such a unique first that we found as part of such a survey, a routine survey at NASA.
Anyone else that's...
Again, just going outside of what NASA does, we are building, the large synoptic survey telescope, which will scan the whole sky every 3 days, and that will provide information that we can provide to NASA as well. So there is, as you can understand, there is continued coordination. I mean, the asteroid that came in from the outside was actually found by a telescope in Hawaii, ground-based telescope initially, and then followed up with NASA's assets, including Hubble and other things. And so we're very aware. And of course, the Wide Field Survey Telescope will also have the capability to survey wide areas of the sky. So we're going into this generation of telescopes that can take enormous images of enormous swathes of the sky, which is, of course, what you need to find these rare objects that may be coming our way.
That's it. And, Mr. Chairman, I've never talked to a scientist who said, oh, no, we're never going to have a big asteroid hit the world. Not one. And not one has ever said, no, we're not, it's impossible that we wouldn't know about it 10 years down the road. Well, that's just not, I mean, they all understand that tomorrow, because of what we have not done so far, we could be surprised to find out that most of the Earth would be destroyed within a short period of time, within a year or two. We need to make sure we change that reality. That should be one of our primary goals, is that the Earth isn't going to be destroyed, for Pete's sakes. And I think that space-based telescopes are going to play a major role in protecting us from that danger, from that ultimate danger. Thank you, Mr. Speaker.
Yes, sir. Thank you. And my ranking member over here, Mr. Barrow, said he wanted to ask one question.
And I'll make it quick because they called votes. Dr. Mountain, you said 1 to the 23rd. So as I wrote this out, that's a lot of potential planets that are out there. Last year, Kepler discovered 1,284 new exoplanets. And the total number of exoplanets that we've discovered is about 2,325, is that? And 9 of which are potentially in the habitable zone. So part of what we're trying to do, the occurrence of life is a rare event, right? And just from my understanding, we're trying to cast a wide net to see as many of these planets as possible. Is that correct, to identify,
Yes, the 1 with the 23 zeros is our estimate of all the number of stars in our entire universe. Within our galaxy, we believe there's 100 billion stars. And now from the observations of Kepler, just by extrapolation, we believe that most of those have planets. What we can see with our telescopes is only out so far, but we believe that we should search all nearby because we believe there are a lot of planets. What we don't know is how many of them have life. But we are going to try and, with TESS, with WFIRST, with all the things that we're doing with our assets on the ground, we're going to try and cast that net as widely as we can because life may be extraordinarily rare. We just don't know what that number is. Biologists will argue that even with 1 to the 23, life is still, we could be it. I mean, there are good intellectual arguments from the biology side. We would like to resolve that by going to observe.
Thank you.
Yeah, fascinating. I also have one, and I think Mr. Rohrbacher's got one as well. We still have about 10 minutes. This is for Mr. Young. Would a congressionally mandated cost cap for WFIRST instill cost, schedule, and requirements discipline? Would it be satisfactorily done?
I actually don't think so. I'm not a fan of cost caps.
Okay.
I think the better solution is what NASA's doing, and that is understand the requirements and the cost and risk and technical complexity requirements that exist now and adjust those to be what we collectively believe to be affordable and appropriate for WFIRST mission, and then to, in a rigorous fashion, control them as we implement the program.
Okay, thank you. Mr. Rohrbacher.
Yes, and I realize that space telescopes are going to play a really important role in our search for intelligent life somewhere in the universe. We have to cope with the fact that we're trying to find intelligent life here in Washington, D.C. right now, so especially on budget issues. I'd like to ask Mr. Zurbuchen about what about the NEOCOM project, and how does that fit in with the space telescopes and the asteroids that I was talking about?
So NEOCAM is an extended Phase A type of project that we funded out of the Planetary Discovery Program, which is actually where we're learning through that Phase A what it would take to get to the congressionally mandated numbers of covering these objects that you talked about earlier within a given number of years. So the NEOCAM is one of the actual designs that would do so. There's a couple other things we're looking at with also smaller spacecraft, but very much in the spirit of NEOCAM. So we're looking at that right now as we go forward and plan.
But you're saying that program is under consideration but not decided upon yet?
We, at this moment in time, we don't have a budget line or anything at this moment in time that would basically allow us to fund that as part of this. Right now, we have our planetary defense budget of that you talked about earlier, kind of in its integral is of the order of $50 million a year. And kind of a NEOCAM, if you look at the numbers, it's closer to the $500 million type of dollars in round numbers. Of course, it may be 50 million less or more.
Just a thought, and one major strike, and any type of thing we do to give us some notice or try to knock an asteroid out of the path because we got enough. We have enough warning would certainly be worth any investment we could make.
Okay, thank you, Mr. Rohrbacher. We are down to 7 minutes, so we need to, I want to thank the witnesses for their very valuable and fascinating testimony, and all the members for their questions. I'm sorry, did you have some?
No, I was just going to do the math. How many times does 50 million go into 1.5 million?
Well, there's a bunch of smart guys right here. Y'all come up with that. Anyway, the record will remain open for 2 weeks for additional comments, and we would appreciate that, and written questions by the members as well. So with that, this hearing is adjourned. Thank you so much.